Welcome back to the final lecture for Math 2610, and thank you very much for sticking with me this far. So this lecture is going to wrap up some of the things that we've seen into a very practical example of something called PageRank. Or, as we can see, this is how to become a billionaire with linear algebra, with the things that you've seen so far. So here's the idea of PageRank. This is used in prioritizing websites. So the idea is that you have a collection of website pages and you want to figure out which ones are more important or more authoritative than others. So the basic idea is that the importance of a page depends on the number of other pages that talk about it. So it's a fairly basic idea that the more interest there is in something, the more important it is. So we can interpret this mathematically by saying that if we have a couple of web pages and web page 1 points to web page 2, in other words, it talks about it, and in a website, how do you talk about it? You have a link. So if web page 1 has a hyperlink to web page 2, we count that as a vote, that web page 1 is saying, web page 2, I think that web page is important. It's important enough for me to include it in my content, so I'm going to vote for it. That's the general idea behind it. But now here's a little wrinkle in it. If it was just the number of votes, you could just count the number of votes out there. It would be pretty easy for somebody to create thousands or millions of web pages that all talk about one page, and suddenly this page becomes more important than anything else on the web. But we're going to throw a little wrinkle into it by saying, well, if a page is already important, then a vote from an important page has more value than a vote from an unimportant page. So if somebody goes out and creates a whole bunch of spam pages with spam links, their value is going to be very tiny. But if you get a vote from an important page, from a news site or a government page or a university page, for instance, that's an important page. So that vote is going to be worth more. Now the question is, how can we encapsulate this mathematically to bring together this ideas of importance? Because if you think about it, what makes a page important? It's votes. What are important votes? From important pages. How do you know those pages are important? They're pointed to from other important pages. So there's a bit of a cyclical thing going on here. How do you figure out when something is important or is authoritative when that authority is what determines its importance? So how do we do this mathematically? Here's an example. Let's say that we have 4 web pages. So we can portray graphically with 4 web pages how they point to each other. Okay? So the entire web consists of 4 pages here. And this is saying that page 1 has a hyperlink to page 2, to page 3, and page 4. Page 3 only has a hyperlink to page 1. So the arrows here are indicating votes. So page 1 votes for 3 pages. Page 3 only votes for a single page. So we can portray graphically what the voting is. But now throw on top of it the idea that of equality of votes right now. So every page has 1 vote. So the fact that it points to 3 pages means each of those 3 pages gets a third of your vote. Okay, so page 1 is giving a third of its vote to each of those pages. Page 4 is giving half of its vote to each of pages 1 and 3. Okay? So every page under this concept has 1 vote. So this is getting at the idea of kind of the importance and the number of votes, but it isn't really bringing in the idea of important pages have more value to their vote. But what we can do now is take these votes and put them in a matrix. So you can see we're getting towards matrices now. So the first column of our matrix is for page 1. And it tells you that page 1 is giving a third of its vote to each of pages 2, 3, and 4. Note that the diagonal on here is all zeros because a page can't vote for itself. So we've got this matrix A that is saying how each place wants to vote. But now we have to work in that important pages have more authority to their votes, so their votes are worth more. So we're going to start with a vector, this general vector, which is going to be the importance of each page. So right now it's unknowns. So x1 through x4 is going to represent the importance of each page. What we are going to do now is say, okay, if a page has a certain level of importance, we're going to say that it has that many votes. So if the importance of page I is xi, then we're going to say that that should be xi votes. So the importance is going to be the number of votes that it has. Then what do we have? Mixing V's and X's here, but so page 1, if its importance is VI, 1/3 of that value goes to is transmitted to page 3, 1/3 of it to page 2, and 1/3 of it to page 4. So now we have this conceptual idea of the importance of a page, and it's distributing that amongst everything else it thinks is important. So now, instead of looking at what it's giving out, look at what that is that each page is taking in. So you look at all the arrows pointing to x1. What do you have? You have all of the value of x3's vote plus 1/3 of x4's vote. So that is the importance of x1. Page x2, there's only one thing pointing to it, so it's going to get 1/3 of the value of x1. And you keep going down here, all of a sudden look at what you have. You have a system of linear equations. And this we can solve. So take this system of linear equations, which we've determined by looking at this graph and looking at the amount of votes that are coming into each one, weighted by the importance, write it as a matrix vector product. And here's what we have. Our vector of importance is equal to some matrix times some other vector of importance. Or write it simply as V equals AV. Now notice what this is. This is eigenvectors and eigenvalues. So this is the eigenvalue, sorry, this is the eigenvector, V is the eigenvector associated with the eigenvalue of 1. So eigenvector for A associated with the eigenvalue, I wrote those backwards, associated with the eigenvalue for lambda equals 1. So everything we've done about eigenvectors and eigenvalues can be used here to show what the importance or the authority of each page is. When you take this specific example and solve it out, you get this. So now you have a value of importance of each of the pages. You have that page 1 is the most important, followed by page 3, followed by page 4, and finally page 2 is the least important. So PageRank is giving you the the importance of each of the pages using this relatively simple idea, which then we solve using eigenvectors and eigenvalues, something that we have seen in this course. So in this example, we get that as an answer. Why do I call this a billion-dollar idea? Because two men named Larry Page and Sergey Brin came up with this idea in 1996 in Stanford University. They patented it in 2001. From this idea, they've built Google. This was the basis of the Google search engine. Now there's a lot more than just this that goes into it, but this is the core of the Google search engine. And I'm old enough to have been around when Google came, and it was a huge revelation in indexing the internet and finding things on the internet. From this simple idea, they have built one of the biggest companies in the world. So thank you for your attention during this class. I hope you've learned something. I hope you enjoyed this to some level. And thank you very much for your time.